Hello everyone, welcome back to Regents Chemistry Review Series. In this video, we are going to talk about acids and bases. So let's start off with the very first theory of acids and bases. So according to this theory, an arrhenius acid is any substance that produces hydrogen ion when as the only positive ion when it's in a solution. So the thing with hydrogen ion is that it's very unstable. So if we have that hydrogen ion in an aqueous solution, it very quickly reacts with water to make H3O positive, which is called the hydronium ion. So the presence of a hydrogen ion or a hydronium ion in a solution is an indication of an acid. This is what the reaction looks like between water and H positive. And an Arrhenius base is any substance that produces hydroxide, OH negative, as the only negative ion in the solution. So we are given some common acids and some common bases in the reference table packet. So common acids are given in table K. And as you can see, most of those acids have the hydrogen ion. So that's like the most positive ion, most common ion between these acids. If we look at the common bases, which are given in table L, we see hydroxide ion as the most common ion. But then we also see NH3, which is kind of like an exception to the hydroxide rule, and that makes us wonder what is what is NH3? How is that a base? Why is it under common bases? And same thing with this CO2 that is written in table K. It makes us wonder because it doesn't have a hydrogen, so why is it written as a common acid? So this leads us to this alternate theory of acids and bases, which was another theory that defined acids and bases. So this theory said that an acid is a proton donor. So that means an acid should have a proton, of course, to donate, but then the base is the proton acceptor. So this one didn't say anything about the hydroxide. It said that a base is any substance in the reaction that is going to accept the proton. So here we are given an example that we are going to look at to see how it works. So as you can see, if we focus on HCl, we see that HCl converts into the chloride ion. So that means HCl has lost or it has donated its H positive ion or the proton. By the way, H positive is called a proton because a hydrogen ion only has one electron. So when it becomes hydrogen atom. So this is your normal hydrogen atom, right? So when it becomes the H positive, it loses that one electron. So now it's only left with that nucleus, which has a proton. That's it. So the neutron only has a proton. So that's why another name that we use for H positive is a proton. Okay, so the HCl in this case is donating its proton. That means HCl is the acid. And then if you look at the H2O, we see that it's becoming H3O positive. So that means H2O is accepting the proton. So that is a base. Now, we have this concept of conjugate acid base pair. So in this case, your conjugate acid base pairs are going to be HCl, NCl, and then H2O and H3O positive. And that's because a conjugate acid is referred to whatever the acid converts into after it donates the proton. And conjugate acid refers to whatever the base converts into after it accepts a proton. So because HCl is converting into Cl minus, so Cl minus is the conjugate base. So this is your acid. This is the conjugate base. So the HCl and Cl minus, that is one conjugate acid base pair. So if a question asks for a conjugate acid base pair, you are looking for either an option that has HCl and Cl minus, because that's a pair, or you're looking for an option that has H2O and H3O positive, because this is a pair of a base and its conjugate acid. Okay, let's do some practice with this concept. So here we have another example. So here we notice that H3PO4, which is phosphoric acid, is converting into H2PO4 minus. So this one is donating a proton, so that means H3PO4 is the acid and H2PO4 minus is its conjugate base. Then, so that's a conjugate acid base pair. Then we see that NO2 minus is converting into HNO2. So that means NO2 is accepting a proton, so that's a base, and then HNO2 is its conjugate acid. So together, both of them are a conjugate acid base pair. Okay, so here is another example. So we see that the weird thing about this example is that both of your reactants are water molecules. So we see that one of the water molecules is donating a proton and it's converting into hydroxide. So that is an acid and its conjugate base. The other water molecule is accepting a proton and converting into H3O positive. So that is the conjugate acid. So for a substance like this, water is one of the very few examples that are examples. Water is one of the very few examples of this type of substance that we call amphoteric. So amphoteric is any substance that can act as both an acid or a base depending on what is it reacting with or what is it making a solution with. Okay. So let's talk about some properties of acids and bases. So acids are electrolytes, meaning that when they are dissolved in water, when they're in aqueous solutions, then they are good conductors of electricity. And that's because most acids, when they are making aqueous solutions, they can dissociate into ions. So electrolyte is a very specific word that we use for anything that can conduct electricity when in solutions. So solids cannot be electrolytes. They are just good conductors if they are good conductors. All right, so if we have a greater concentration of an acid, meaning it's going to be a better conductor because that means we are going to have more ions in the solution. And if something is a good conductor, then that means it's a strong acid. If any acid is a poor conductor, then that means it's a weak acid. So another property of an acid is that it turns blue litmus red, and the pH of all of the acids is less than 7. They do have a very high concentration. The reason why pH is less than 7 is because they have a very high concentration of hydrogen or hydronium ions. So pH depends on the concentration of the hydronium ions. So the less the concentration of hydronium ions, the greater the pH, and the more the concentration of hydronium ions, the lower the pH. And acids taste sour, they are corrosive, which is why we can use them to clean substances. And then they can also, this is a very important property, acids can react with metals to produce hydrogen gas. So for example, we can have HCl react with magnesium, which is a metal, and this can produce magnesium chloride, which is just an ionic compound, and it can produce hydrogen gas. And we're gonna have to balance this. Okay, so let's talk about some properties of the bases. So bases are also electrolytes, meaning when they are in solutions, they can conduct electricity. So if we have a greater concentration of a base, it's a better conductor. So good conductor means a strong base, poor conductor means a weak base. They turn red litmus blue and they have a pH normally greater than 7. So because the pH is greater than 7, that means they have very low concentrations of hydronium and instead they have high concentrations of hydroxide. So bases taste bitter and they feel slippery or soapy, and bases are very caustic, meaning they can dissolve the skin. So unlike the popular opinion, most bases, especially the very, very strong bases, can be way more dangerous than the strong acids. All right, so some properties of the salts. Salts are diionic compounds that have the positive and the negative ions. So the thing about their positive and negative ions is that their positive ion could be any ion out there other than the hydrogen ion, and their negative ion could be any ion out there except the hydroxide ion. because if something has a hydrogen ion as the positive ion, it's an acid. If it has hydroxide, it's a base. So NaCl is a good example of a salt. This is your table salt. We have sodium ions and the chloride ions. Salts are also good conductors when they are in solutions. So they are also electrolytes. Just one very quick thing to remember as you are trying to identify your acids and bases is that there are some organic compounds that look very similar to acids and bases, and they can make it kind of hard for you to differentiate between acids and bases. For example, we have organic acids that have the functional group COOOH, so they are drawn like this. Now, they do have that OH, which can make you think that this is a base because it has a hydroxide. However, this is a functional group for an acid. So be very careful with that. Now that we know the organic acids, it should be easier for you to identify. And then same thing with another type of organic compound, your alcohols. They also have the OH, but they are not bases, even though they have that hydroxyl group. So for you guys, for the Regents exam, the best way to kind of get around this, because we kind of talked about organic compounds, but not in that much deep depth. So just focus on the acids and bases given in table K and L, because those are the most common types of acids and bases that are going to show up on your exam. So if you kind of don't see anything there, that means there is a chance that it might not be an acid or base. So you might want to check your table for the functional groups, table R as well, to see if it could represent an organic compound. Okay, so let's talk about neutralization. So neutralization is a reaction that happens when we combine an ARRHENIUS acid and a base, and as they combine, they make salt and water. So let's take some examples. Here we have sodium hydroxide combining with nitric acid. So let's focus on this one first. When you are asked to write the products of a neutralization reaction, remember that one of your products is water. So the first thing that you would want to do is take out the water. So I'll go ahead and separate the hydrogen and the hydroxide and combine them to make water. What this does is it makes it easier for you to determine what is your salt, because you just look at the ions that are left. So I'm left with sodium and I'm left with nitrate. So you're going to go ahead and just combine those two, and your salt is going to be sodium nitrate. Just some of the things to keep in mind, because this is an ionic compound. Remember that you write your positive ion or the cation first, followed by the negative ion. And remember that you want to make sure you have the correct formula. So check your charges. So sodium has a charge of, and subscripts. Sodium has a charge of +1. Nitrate is a polyatomic ion. So you can look at table E to figure out the charge. So nitrate has a charge of -1. So if you do the crisscross, sodium gets a subscript of 1, nitrate gets a subscript of 1. So that means this formula that we wrote is correct. So let's look at the second example here. Once again, we're going to go ahead and take out the hydrogen and the hydroxide to make water. The thing to keep in mind here is that you have 2 hydrogens and 2 hydroxides. So that means when they combine, they are going to make 2 water molecules. So now let's look at what's left in your compound. So we have 1 calcium and we have 1 sulfate. So before I write the chemical formula, I'm going to look at the charges. So calcium has a charge of +2. You can get the charges from the periodic table. So calcium has a charge of +2, and then sulfate is a polyatomic ion which has a charge of -2. So when you do the crisscross, both of them have a subscript of 2. We can simplify that. And so your formula is just going to be CaSO4. All right, so this is how you complete your neutralization reactions. So let's talk about pH next. pH is a kind of something, a of a scale that we use to determine how acidic or how basic a substance is. So it's a logarithmic scale. If we have a pH that is less than 7, then the substance is acidic. And the lower the number is, the more acidic that substance is. So if you're comparing something with a pH of 1 to something with a pH of 5, the substance that has a pH of 1 is much more acidic than the one with the pH of 5. The pH of more than 7 is basic. So once again, in this case, the higher the pH, the more basic that substance is. So the substances that have a pH of 14 are very, very strong bases. And that's because pH of 7 is neutral. So the farther away the substances are from that neutral pH, the stronger of an acid or a base they become. So here's the equation for the pH. It's negative log of the concentration of H positive. So if I give you the concentration of H positive, you can just plug in this equation in your calculator to like figure out the pH. But there's also a shortcut that we learned in class. So here I gave you the concentration of H positive. Let's say that's 1 times 10 to the power of negative 5. So the shortcut is that if your given concentration is a binary number, so something that looks like this, where your coefficient is a binary number, it's just 1.0 times 10 to the power of negative 5. For something like this, we can use a shortcut and we can just say that the pH is the absolute value of the exponent of the concentration. So the exponent of the concentration is negative 5. If you take the absolute value of that, it's your pH is going to be 5. But once again, the thing to keep in mind is that it only works if your coefficient is a binary number. But if I give you something like 5.0 times 10 to the power of negative 5, then this shortcut is not going to work. So for something like that, just plug it in the calculator. Okay, so remember that if we change the pH by 1 unit, that is going to change the concentration by a factor of 10. Okay, so here's what we mean by that. If, let's say, I am going from a pH of 1 to a pH of 2, we are increasing the pH. So that means your hydrogen ion concentration is going to be lower, because remember, pH and hydronium ion or hydrogen ion concentrations are indirectly related to each other, and that's because the lower the pH, the more acidic the substance is. So hydrogen ion concentration is going to be less, but how much? Because we are changing the pH by 1 unit, hydrogen ion concentration is going to be 10 times less. Okay, if I go ahead and change my pH from, let's say, pH of 13 to a pH of 11. So this time we are decreasing the pH. That means hydronium ion concentration is going to increase. But because we are changing it by 2 pH units, so that's going to be 100 times more. Okay, so pH of 1 to 7 represents the acids. So for acids, the hydronium ion concentration is greater than the hydroxide ion concentrations. For a pH of 7, it's just neutral. That means hydronium ion concentration is equal to the hydroxide ion concentration. And for a pH of 7 to 14, which is a base, hydronium ion is going to be less than the hydroxide. So let's do some math for the pH and pOH. So pOH is going to be the concentration of hydroxide instead of hydronium. So we just take the equation for pH and substitute OH instead of hydrogen. So the shortcut here is that, once again, if your hydroxide ion concentration is a binary number, then the pH is going to be the absolute value of the exponent. And one quick thing to remember is that your overall pH scale is 14. So the pH and pOH is going to add up to 14. So if the pH is 3, then the pOH must be 11. And same thing for your hydrogen and hydroxide ion concentrations. They should add up to 1 times 10 to the power of negative 14. So if the hydroxide ion concentration is 10 to the power of negative 6, then hydrogen ion must be 10 to the power of negative 8. So if I ask you what is the pOH of 0.001 molar hydrogen iodide solution, so you are given the hydrogen iodide, which has the H positive ion. That means this is an acid. So your hydronium ion or hydrogen ion concentration is going to be 10 to the power of negative 4. We can go ahead and plug that in the pH equation. And if we take the absolute value of the exponent of the concentration, then the pH is going to be 4. But because the question is asking for the pOH, we're going to do 14 minus 4, so the pOH is going to be 10. What that means is that the hydroxide ion concentration is going to be 10 to the power of negative 10. So once again, remember that the hydrogen ion and the hydronium ion must add up to 10 to the power of negative 14. All right. Indicators. Indicators are something that we can use to figure out the pH of any given solution, and that's because these substances change their color over a very narrow pH. So what's very, very important is for us to know how to read table M. So if we look at bromethymol blue, the pH range here is 6.0 to 7.6, and the color range is yellow to blue. What that tells us is that if we add bromethymol blue to a solution and the solution turns yellow, that means the pH of that solution is 6 or less than 6. That means it's an acidic solution. If we add bromethymol blue to a solution and it turns blue, that means the pH is 7.6 or more than 7.6. However, what if we add bromethymol blue to a solution that has a pH between 6 and 7.6? In that case, our solution is going to turn green. So the color between yellow and blue. And pretty much the last thing about acids and bases that we discussed in class was the titration, the technique that we can use to find the concentration of an unknown acid or base if we are given the concentration of the other substance. So and we use the difference in the volume to do that. So here on the side you see kind of a quick setup for titration. So this is the practical application of neutralization. We apply the concept that when acids and bases combine, they neutralize each other. And so if we add an indicator, we can see the changing color that can help us determine that now we have a neutral solution. And kind of determine the concentration of the other thing. So the solution that has a known concentration is called the standard solution, and the one that we don't know the concentration of is just the unknown. We use an indicator to figure out the endpoint or the equivalence point. So make sure that we know the difference between these two. Technically, it's the same point in the experiment. However, they are defined differently. So endpoint is the point when the moles of the hydrogen ion is equal to the moles of the hydroxide ion. So this is more of a mathematical point of view. And equivalence point is kind of a visual point. So this is where we see the color change, and this is where the color indicates that we have now reached neutrality and that we have a neutral solution or equal amounts of acids and base in our solution. So very quick review of how titration works. So in our flask, we put the substance with the unknown concentration, and then we put a few drops of the indicator. The most common indicator that we use for titration is phenolphthalein, so about 2 to 3 drops of that. And then we fill the BURET, so this long tube that I hope you all remember. So we fill this BURET with the solution that we know the concentration of, so your standard solution. So we want to fill the burette kind of to the top, but also we don't want to cross the 0 mark. And then we take our initial volume, and then eventually we are going to just run the standard solution slowly. So turn on the stopper and start mixing the two solutions. Eventually what's going to happen is that the color is going to start changing, but we keep swirling it until the color change is permanent and it doesn't go away. And then remember, our goal was always to get the lightest pink color, as light as possible, because the more pink your solution is, the more basic that solution will be. So once the color is constant, that means we have reached the end point. So that's where we stop and we take the final volume. So that gives us the difference in the volume, or the volume of the standard solution that we have used. So very quick review about reading the volume. And this is something that can most likely show up as a question. So remember, for the burette, at the top we saw 0 milliliter. So we had 0 milliliter at the top, and then we had like somewhere around 50 milliliter at the bottom. So that means as we were going down the volume, the numbers were increasing, right? So in this case, we are going from 15 to 16 here. So when we are reading a burette or a graduated cylinder, just anything that has like a closed long tube and where the liquid forms a meniscus, remember that we have to read the bottom of the meniscus, okay? So in this case, it's going to be read as 15.567. So we know that we definitely have a 15.7, and then the number after that is kind of up to everyone's discretion, because that's like your estimated digit. So some of you might say 15.74, some of you might say 15.75, someone might say 15.73 or 15.76. All of those are right answers. But remember to read the bottom of the meniscus. Okay, so now let's talk about the calculations, because we collected the measurement from the titration, right? So we have this is the equation that we use for titration. It's given in table T. So MA represents the molarity of the acid. VA is the volume of the acid, MB is the molarity of the base, and VB is the volume of the base. So if I give you this question, what is the molarity of HCl if 10 milliliters of 4 molar sodium hydroxide neutralizes exactly 20 milliliters of HCl? What this question is telling you is that if you think about your setup, in the burette, you had the sodium hydroxide. And more specifically, you had 4 molar sodium hydroxide. And when you read that volume from the burette, that difference in volume was 10 milliliters, because you used 10 milliliters of your sodium hydroxide. And then in the flask at the bottom, wow, that is a very bad flask, but okay, in the flask at the bottom, you had 20 milliliters of HCl. Okay, so we need to figure out what is the molarity of that HCl that we had in the flask. So we just go ahead and fill in all of the information that we know. Molarity of the acid is unknown, so we set that equal to X, and then just plug in your numbers, calculate for X, and that gives us 2 molar as the molarity of the acid. So here's another question. What's the volume of 6 molar sodium hydroxide that will be, or what volume of 6 molar sodium hydroxide will be required to neutralize 10 milliliter of 5 molar HCl? Once again, whatever is unknown, we set that equal to X, and then just solve for X. All right, and so that is pretty much all that we need to know about acids and bases. Good luck. I will see you in the next one.